Okay, so we just talked about what these different situations are, so now let's look at how to use them. So we are looking at the limit as x approaches infinity of this function right here. So we want to look for the degree. So what thing is moving the fastest? When we are looking at things that are in what we would consider standard form, but maybe not in the highest exponent to lowest exponent, we are looking for the highest exponent on top and the highest exponent on bottom. If I'm looking on top, the highest exponent is 5. If I'm looking on bottom, the highest exponent is also 5. So this would be what we would call an EATS DC case. So our exponents are the same. We are going to be dividing the coefficients. So we need to remind ourselves the sign of the coefficient also goes with it. So the number in front of x to the fifth power is negative 10. The number in front of x to the fifth power in the denominator is negative 15. So I have negative 10 over negative 15. This reduces to 2/3. So what this tells me is my limit is going to go to 2/3. On the other hand, when I have something that is in factored form, we need to be a little bit careful. Thankfully, we don't need to look at what the degree is overall. We just need to make up an answer, right? So when I'm looking here and I'm looking at factored form, what I want to look at is all of the x's, exponents, and we're going to add them together. So the degree on top is going to be 3, while the degree on bottom is going to be 2. If we were to multiply it out, then we could look for just the highest exponent. So the degree on top is 3 and the degree on bottom is 2, so this is a botno case. It's bigger on top, so there is no horizontal asymptote. So now we might just want to figure out what direction that we're going. So if I was going towards positive infinity and I'm looking here, I have a positive value that I'm adding 3 to. But if I have a really, really, really large number, like 10,000 for instance, this positive number is going to be way bigger than this. So it wouldn't matter how much we're adding to it. If we square that really big number and multiply it by 5 and add to it, it's still going to be positive. So the entire portion on the top is going to go towards positive infinity. On the other hand, when we look at the bottom, this is going to go towards positive infinity because there is nothing with it but a positive 5. And 3 minus 5x. Well, 3 is not a very big number, so if I am subtracting a ridiculously large number from it, then I know that this piece right here is going to be negative. It's going towards negative infinity. So because I have a positive infinity on top and a negative on bottom, I know that these are going to be going towards negative infinity. Okay, so we're going to look at these next ones. So I have the degree of the top, so the highest on top is 4, the highest on bottom is 5. So it's bigger on bottom. So this would be a Bobo case, which means this will equal 0. Looking for the top, I have the biggest exponent of 5. I have on the bottom the biggest exponent of 4. It's bigger on top. So botno. If this was a multiple choice question and the answer was does not exist, we could absolutely go there really easily and know that that's the right answer. If I look here, I have a very, very, very large value here that is being kind of taking the lead here. So it is probably going to go towards negative infinity. Okay, now we're going to look at this polynomial divided by a logarithm. So we have the limit as x approaches infinity of x to the 64th power divided by log base 3 of x. So we need to kind of remind ourselves of the order of magnitude for these functions. A polynomial is a thing that is going to grow faster than a logarithm. So that means that the top is going to grow faster. So this is another botno case. When I raise something to the 64th power and it is positive, it's going to stay positive. And when I take the log of something, it is also going to be positive unless I'm really, really close to 0, but we are not because we're going towards infinity. So this is going to go towards positive infinity. we have negative 7x to the 30th power, negative 10x to the 27th power, plus 3 to the x power. Well, if we were just looking at the polynomials, the x to the 30th would win, but because we have a 3 to the x power, that is going to kind of win out in this battle, which means that this is a Bobo case. So we have a 0. We have minus 4 natural log of x minus 9x to the 31st power divided by 5e to the x. Looking at our order of magnitude, logarithms are the smallest, then polynomials, then exponentials. E to the x is an exponential, so the denominator is growing fastest. So it is a Bobo case, and it equals 0. When it's pretty straightforward like this, these take very little time, but sometimes we get into ones that are a little bit harder. So we have one that looks something like this. This is going to cause us some issues. So realistically, what we do is we still look at the highest exponent, but we're going to kind of look at it a little bit separately. So if I'm plugging in really, really large numbers, this x to the 4th is making nowhere near as an impact as this x to the 12th. So we're going to be realistically looking at the limit as x approaches infinity of the cubed root of 8x to the 12th. The 8 doesn't really matter that much either, but we can kind of put it in here. And then we're looking at 3x to the 4th. That plus 10 doesn't do anything for us. Well, we're going to go ahead and switch this around into something that has a fractional exponent. So to kind of remind ourselves, fractional exponents come from when we take something like 3x to the 12th and we turn it into x to a singular power. The number that always goes on top is the original power, so in this case 12, and the number that goes in the denominator is the root, so 3. So I know that this is going to be 8x to the 12 over 3 divided by 3x to the 4th. This is going to give me the limit as x approaches infinity of 8x. 12 divided by 3 is 4 over 3x to the 4th. These are now the same exponent, which means our overall is an HDC, and we divide those coefficients. So our limit here is going to equal 8/3. Okay, we're going to do the same thing here. If I were to look at this when it's a square root, we know that root kind of goes with the number 2. So when I'm looking at 9x cubed and it's square rooted, this is really what am I doing? The cubed root of 8. This needs to be the cubed root of 8 over 3. Because I am rooting the 8 and the 12, not just one of them. So I need to square root both the 9 and the x cubed. If we square root the 9, it's not too bad, but we can kind of change this into a fractional exponent. So if we look at this, this is one of these properties that we can do with square roots as long as we are multiplying inside them. So the square root of 9 is equal to 3. And if we change this to a fractional exponent, we get 3 as the power and 2 as the root, so 3/2. If we look here, 3/2 is just 1.5. So 1.5 is the largest exponent on top, 2 is the largest exponent on bottom, so this is a Bobo case. So this equals 0. So we like these methods, even though some of them are a little bit tricky and may require some extra thinking. These are faster. So why do we want to use horizontal asymptotes? Well, here is what they would have done a long time ago. In order to get an answer to a problem like this, they would have had to look for the highest exponent possible out of everything. In this case, there's 5 on top and bottom, but if there was only one on top or bottom, it would still be 5. So what we're going to do is we are going to take this limit and we are going to divide everything in the top and everything in the bottom, which makes this a special form of 1, by that highest exponent. So we get something that looks like this unfortunate mess. I can do this because as long as I do the same thing to the top and bottom in the exact same way, then we are just doing a special form of 1. So one thing I can remember is that if I do this to everything in the top and everything in the bottom, I can do and separate them, so I can divide each individual term by x to the 5th power. So if I do that, I'm going to get 8x squared divided by x to the 5th minus 10x to the 5th over x to the 5th, all divided by 4 over x to the 5th, 3x cubed, x to the 5th, 20x squared, x to the 5th, 15x to the 5th, divided by x to the 5th. Now that we have this, we're going to go ahead and simplify this. So I'm going to go ahead and the limit as x approaches infinity. X squared over x to the 5th means that we're going to have 8 over x cubed. X to the 5th divided by x to the 5th is 1, so that 10 just kind of chills out. 4 over x to the 5th doesn't change at all. We have x cubed divided by x to the 5th, so we get 3 over x squared. X squared divided by x to the 5th means x cubed, and then x to the 5th divided by x to the 5th, giving us 1, leaving us with that coefficient of 15. So the thing is that when we look at it this way, every single one of these has an x in the denominator now that has a fraction, otherwise it is a whole number. So one of the things that we have to remind ourselves is that when we have a limit that's approaching infinity and we have a number divided by 0, when we have a number divided by something that's really, really big like infinity. So we're looking at something like this. That's going to go to 0. So essentially, that is going to be 0. This is going to be 0. That's going to be 0. This is going to be 0. So realistically, what this leaves us with is this fraction that is 0 minus 10 and 0 minus 0 plus 0 minus 15. So negative 10 over negative 15, which gives us our 2/3 being positive. So we could do all of this, and I can even add more steps of separating the limits out even more, but this is kind of the process that people went through before. So if we can use horizontal asymptotes and those horizontal asymptotes rules, where BOTNO, BOBO, ECC are just acronyms to kind of help us out, we can kind of get through it faster. So thank you for sticking around and watching these videos. Don't forget to smash that like button, subscribe, and ring the bell for notifications.